Okay, so after orientation, the second thing we are interested in, as I said, if we have this inclined slope and we have our, block, we need to know what is the cohesion and what is the friction angle, or maybe the what is the resistance force, right? So what is the resistance force? That we need to know so that we can design, the ways that is forming, or maybe the design the support system for the ways that is forming. So for that, first let's see what are the testing machines we have. So the second year students, mining student, we recently learned this in our rock mechanics lab. If you remember that, I'll quickly, tell about this. So we have this thing is which is called our direct shear testing machine. So here there are a few things. First thing is this, the rock which is there. So this is the rock, and this is your joint. This is the rock. This is the joint. So these joint properties we are trying to find it out. So what it does, I think is difficult to imagine the three-dimensional picture. So, but what it does is it is confined within this bottom kind of holder here and the top holder here. So top part of the rock goes here and the bottom part goes here, so that the joint is touching to each other, right? And then what we do is there is some kind of lever kind of arrangement here where this one. So where what we do is if we put more and more weight, so this lever gives a force in this direction, and this transfers this load from here to the wall kind of thing here. So it applies a vertical load to the upper part of the sample. So this upper load which is given by this ball is called our normal reaction. Normal force or normal reaction, right? This goes to the top part of the block. Let's say this is our block and this is our top part. So we are providing some load. So if you increase this load more and more, you can change the normal force on this joint specimen. Then what we do is we have some arrangement where we can give a force, horizontal force to the bottom part of the this holder. Okay, so and when this whole the bottom part moves, there is something called a load cell. Okay, which tells us what is the load. So first thing what we do is we keep the specimen and its place. Second thing, basically what we do is apply some normal load. And some normal load. And third thing, we apply shear stress. So this normal load calculation is very similar to our previous one. where, you know, let's say uh, let's say this is geometry. Let's say this is a joint surface. This is a joint, and F is the load. So F divided by our area is your, we call it sigma n, normal stress. Okay, so this is very similar to our UCS test where we had our rock specimen, cylindrical rock specimen. We have this F, so F divided by pi d square by 4 is our normal stress. Okay, so similar to that. Second thing is, let's say what we are doing here is applying some shear load, let's say Fs. So Fs divided by area is your called shear stress. We call it in tau. So this can be in MPa or kPa, right? This will be again MPa or kPa. Is this clear? What we are doing here in this test?
Yes.
Sir, the
Okay.
areas are same for both shear stress and axial stress, or we should change.
Yes, they are the same. They are the same. So what happens, you know, let's say you apply different type of, you know, different magnitude of the normal stress. Okay. So what happens? Let's say this is our normal stress, like we were doing in our, you know, triaxial test. So this, let's say this is our sigma n. So I'll say that okay, I will apply 1 MPa sigma n MPa and see at what value of tau it is filled. Okay, tau is in MPa again. So let's say this is 1.6. If you and what we are doing here, let's say this is your rock specimen which has a joint in between. Stress from the top, and we are trying to see. So at what value there will be a separation? That is what we are trying to find out. So because let's say you apply 0.1 MPa stress in horizontal direction, right? 0.1. Maybe this is not going to move. This will be stable. Then 0.2 MPa, you just increase this load. 0.3 MPa, maybe it will not move. And you just do like that. And at 1.6 MPa, what will happen? There will be a separation between these two, top and bottom. Is this clear? So that
Yes.
load, that 1.6, we are trying to note it down. Okay. So then what do we do? We do it at another, you know, another confinement. Same joint, another confinement we apply, or the sigma n apply, let's say 2 MPa. This is giving, let's say, uh, 2.2. Let's say increase it to 3. Let's say we get 2.8. Okay, so is this clear what we are doing here?
Yes, sir. It's clear.
Okay. Geology students, is this clear?
Sir, yes.
Or do you want me to repeat?
No, sir, understood.
Okay. So now what we do is we plot this in our, let's say if our this is sigma n axis in MPa, and this is tau axis in MPa. Okay, so first point will be 1 versus 1.6. Let's say this is 1 versus 1.6 is this point. Okay, 2 versus 2.2 is, let's say, this point. 3 versus 2.8 is, let's say, this point. I'm sorry. Okay, so and what we do is we join those two lines like with a kind of a straight line, right? Try to get the best fit. It will not be in one straight line, but you try to do it in Excel file. And like in Excel to get the base fit line. And let's say it intersects here. And let's say this value is 0.75. So then our something called like cohesion that we were looking for is your 0.75. Can anybody tell me what is the friction angle here? Because you have already taken these courses, right? So can anybody tell me what is the friction angle? Second year mining students. Anirudh, can you hear me? Can anybody hear me?
Yes, sir, you are audible.
Yes, sir.
Yeah, so what is the friction angle here? How do you get the friction angle? I said that, you know, this y-intercept is your cohesion C, right? This distance, this to this. Right, what is the friction angle? Come on, you just studied
Yes.
2 courses.
So tan inverse slope of that line.
Yes, this is the friction angle is the angle what it makes with this. You can say x-axis, right? So this is your friction angle phi. Phi equal to, maybe this is equal to, let's say, 43 degree. Okay, so let me quickly, tell you what we do here. We put it in this setup called, direct shear test setup. We first put the sample here, okay, and apply the normal load, a particular value of normal load, and see at what value of, this shear stress, there will be a relative movement between these two sides of the joint, right? So that value we try to find out. Then what we do with the first load, we calculate the shear stress, and then we add another weight, and then we add another weight. So let's say we need at least 3, data point to get our cohesion and friction angle. Okay, so we test it at different normal load, and then we have to calculate what is the shear stress, and then we get it. Then we plot it tau versus sigma n, and we get what is our cohesion and what is our friction angle. Is this clear?
Yes, sir.
Okay. So this one we are going to use it for our stability analysis of the wedge. Okay, along with our density. What is density? Can anybody tell me why I need density? Come on. You have taken 2 courses related to rock mechanics in these joints, what we are talking here. See, let's say we have, inclined plane, and we are trying to find what is the chance that this block will slide, right? So we have weight or mg acting. So how do you calculate this mg? Mg equal to density rho v, right? Is the mass into g, or maybe mu mg cos theta, right? So for that, calculate the mass, we need the density and also the volume of that. So similarly, in our, underground design case. So how big is this mass which is sliding? So that we need to know, right? And what is the weight, so that we can calculate what is our resistance force. Okay.
Yes, sir.
Yeah, but this mg, so let's say we are trying to find out what is the factor of safety. We call it factor of safety. So what is the chance that this wedge will slide? So what will be the driving force if this is theta and the mass of this is m? Driving force is what? Come on. Like geology students, can you tell me from your plus two physics knowledge? Mg sin theta, right?
Yes, sir.
Okay. So what is the resisting force? Equal to mu mg cos theta, right? Or maybe you can write, yeah, if there is no cohesion, it is open joint, this is mu mg cos theta. Right or wrong? Let's call it
Yeah.
D. This is our R. So factor of safety is R by D. Okay. But now the question is, if you want to get your, factor of safety, that is our target, if it is within our limit or not, then this mm gets cancelled, right? Then you don't need density. Does it make sense what I'm saying here? I'm surprised. Okay.
Sir,
So
can you
can you?
repeat once?
So what I'm saying is, I said that we need density to, let's say you are designing this wedge, right? So density is one of the things. Along with C and phi, we need the density of the rock also, right?
Yes, sir.
So, but the question is, like, if you divide this, mm get cancelled, gg get cancelled. So sine theta, sorry, mu cos theta by sine theta is your factor of safety. Fos is a factor of safety. So when you like designing something for your civil engineer, mining engineering project, this factor of safety, let's say you are going to keep it 1.5. Okay. So,
Yes,
but
sir.
there is no term of this density here, right? So why we need density then? That was the
So
question.
put support, we need the like what force we need to apply
Yes, yes. So
to
if it
stop.
is less than 1.5, then other terms will come. So let's say, or maybe if cohesion is here, so your resistance is C plus mu mg cos theta by mg sin theta, right? So this into area, C into area plus this. So here we don't cancel, we cannot cancel this m. So that's why we need density, okay? Or maybe if you are providing some support, let's say the support resistance is T, then T plus this thing is, so this is your vector of safety. Okay, we will see this thing. Maybe we'll solve an example and I'll show you this. Okay, so this is how it looks like in the lab. This is that first the wall thing which is loading, transferring the load. This is the place where we add more and more weight, and this is connected to this top part of this loading frame here. So this is the box This is the box where we keep the top part of the specimen and the bottom part goes here. Okay, and this is the loading arrangement. Actually, this. Can you see this?
Yes, sir.
So this is kind of a pump, right? Like this is like if you press this thing, it will apply some more and more load, and that load is indicated here. What pressure you are applying? Okay, so that pressure you can calculate, and gradually it's like pumping. Okay, you just pump this thing and apply more and more pressure and see at what point this whole thing is failing. So you can either apply with this manual kind of pump, or maybe you can automate it, right? Like some automatic pump are also there. Is this clear? Like how this machine looks like? The testing setup.
Yes, sir.
It's pretty simple, but it's useful. Then we have extremely large direct shear testing machine, where this thing can be, the sample dimension can be, let's say, 1 meter. Why we need 1 meter sample? Why not a small one?
Sir, in actual scenario, it can be 1 meter.
The joint means joint, right?
Yes.
So what happens in actual scenario, as you are saying? So the joint may look like this. Okay. So let's say if you test the in the first setup, you test the specimen here, and you test the specimen here, and you test the specimen here. What do you think? Which will give you higher strength? One, two, three. Which will give you the highest strength? If you test, which is the lowest one? Can you just tell me?
Like it will be less rough.
Yeah, which is the least one?
Maybe 2.
Two. How about others? And which is the highest one? Maybe one. No, this is smooth one, right? So it is easier to push in this case. So you are correct. This two is the lowest one, and maybe this depth is more here. So one is maybe the highest, and this is the lowest. Okay, in the intermediate. So what we do, if we take this small sample, let's say this is 10 centimeter. This is 10 centimeter. So maybe here, this case, the friction angle, what we are going to get it 40, 23 degree, let's say. So this will give us a friction angle, let's say 46 degree. And this, what happens, this one here can give us some, let's say 39 degree, right? So which friction angle you are going to take? Are you going to use this one or this one or this one? You will get confused, right? Like what friction angle you'll be taking. If you take from from different location of this, joint plane, the or different sample, then they will give you different kind of strength parameters. Is this clear?
Yes, sir.
So what you will do?
Sir, we will take it completely, then we will test it and get to 1.
Yeah, so this is why we do the bigger one. If it is the project is important, and if it is not within that, within that limit, but if the, let's say the joint is very uniform in all the places. So either you take it here, take it here, take it here, it's the same thing, right? Okay, so in that case, we can use the previous one. But if it is varying and this is different, you cannot take an average of this and take it, right? And how many you will get this? How many of the samples you will get? Okay, so that's why we take a bigger sample to accommodate everything and get a kind of a better result. So this is one of the, yeah, this is in some laboratory in Sweden, rock mechanics laboratory. It's in some, they have some setup in India. See, these are the big, rock specimen. You take it from the site, you cut it and get it from the site, right, and test it. Okay, so let's say you are designing some dam, right? A big dam, let's say. And this dam is resting on a rock foundation. So it's very critical, right? Like if the water pressure is too high, and if it is not good enough to take care of the shear load, then the whole thing will slide and it will kill thousands of people, right? So you need to do a good high quality investigation in these kind of cases. Okay, is this clear?
Yes, sir.
So and then we also do some in situ shear testing. So we take everything in situ. Let's say this is one of the big K1 we are designing. So this is the setup to give you the the normal load, and then it is the some sample is here. Can you see this one? This is the sample. So we don't disturb the sample because when you pour it or you cut it and take it to the laboratory, maybe this get damaged, the joint surface. Okay, so you just carefully cut the sample and then we apply this vertical load. So this is for sigma m, and then we apply some shear load to test the specimen. Okay, to get the properties. So this is called in situ shear testing. Is this clear? Yeah. So see, there's a closer view of that thing. So here we are applying this the shear load using this setup here. Okay. We have different kind of arrangement to see how it is deforming, right, and on. So I hope it is clear. Anybody has any question up to here?
No,
Okay. So yeah, now coming to the laboratory shear test results. So we have different, different type of uh, this joint specimens. Like we have intact weak rock. Okay, we have fractured strong rock, and we have rock clean fracture, and we have smooth clean fracture, and infield fractures. Okay, infield fracture means in between those two joints we have some filling material. And if you plot this tau versus your sigma n, effective normal stress, then this is how they behave, like different type of joints. So if it is smooth clean, you can see smooth clean is this line, right? Let's say this is O A B C E E. So can you tell me what is the cohesion for the smooth clean fracture? Cohesion equal to what? Smooth clean OB line. Can you put it in the chat box? What is the cohesion for this smooth clean fracture? I told you how do you get cohesion and how do you get friction, right? So can you put it in the chat box? Students, I want your answer here. What is the cohesion for smooth, clean fracture?
Sir, there are answers. I think it's not coming in your chat box.
Or is it? Oh yeah, now it is coming. But how about others? We have some 10 answers. Yeah, so those who responded, see, I don't know what you students are doing. Many of you have not, let me note it down. It's responding here. Okay. Yes. So please, maybe I'll give some more weightage to those who are attending the classes seriously, right? So what I was saying is, C is your y-intercept. So if this is tau versus sigma n plot, then this is your C. So in this case, it is just passing through origin. So this is the cohesion value is 0. Okay, but if it is in field fracture, you have some cohesion value, some positive value, right? And this is how they behave. Okay, so we have typically three types of discontinuity. One is rock. Rock means it is the wavy kind of thing. Second is smooth. Smooth is like it's the joint, the interface is almost horizontal, and then we have infield. So if we have two joint surfaces, then we have some filling material here. This green is selected, but okay, so this is filling material, infill. There are three type of joints, right? And as I said, this filling type of joint, it gives you some cohesion, but the smooth and this rock clean joint, they have almost zero cohesive strength or zero cohesion. Is this clear?
Yes, sir.
So this plot here says something a little bit, different thing here. This is shear stress tau versus our shear displacement and normal displacement. What does this mean is when we have rock joint, Eraser is selected. Eraser is not. Okay. So what happens? First thing is normal stress, and we have some normal displacement, and we have some shear displacement and shear stress. Okay. So what happens? When we apply this vertical load to this joint, these two surfaces, like if you see in a microscope kind of thing, it is there is a gap between two joint surfaces. So when you apply this load, gradually this gap reduces. So that displacement, how much it is coming down? Let's say you take a plane here. So what is this displacement? What is this reduction is in this, the distance between these two planes, that is your normal displacement. Is this clear? When you apply, increase this. Okay, so this force divided by that area is your normal space. That is what I have already, discussed. So when we shear this, let's say we started from 0.1 MPS here, 0.2, 0.3, like that. So there is a relative displacement, small amount. That is that is what we get is called our shear displacement. See, this is how what happens. Is this clear? And the shear stress again is tau equal to the shear force divided by area. So these are the four terms. One is normal displacement, one is normal stress, another is shear displacement and shear stress. Anybody has any question about this? Understanding these four terms here. Okay. So this is how it looks like when you do, uh, different, like let's say this part here. Stop. Okay. So let's say this is with a small value of confinement. Okay, maybe this is 0 point or maybe 1 MPa. This is 2 MPa. This is 4 MPa. Let's say. So when you do this kind of test, we get this kind of curve. Okay, so this is shear stress versus shear displacement curve. And what is this value? Is your shear strength for that value of confinement. Okay, so is this clear? How do you get your peak value? So this is a peak value for this thing. This is a peak value for this thing. Anybody?
Yes.
Okay. So you need to take these points because you have done it in rock mechanics lab in the last semester itself, right? So you must be knowing about this. And for now, let's ignore this, normal stiffness and shear stiffness, and just concentrate on this thing. Okay, and then as I said, we use this thing to that those points that we use it to get our C and phi value. Okay, but on top of that, if you want to learn more, you just Google this normal stiffness and shear stiffness kind of thing. I'm sorry, like this OneNote is having some issue here. Okay, so please go through what is written here. Let's quickly finish this. One thing I just want to say, there is something called asperity model, right? It says, let's say you have a smooth joint, and it has this joint has some friction angle, fine, and on top of that, it has some asperity, something going like this. Okay, and this, if you zoom it, looks like, this angle is, let's say, I. Okay, then what this asperity model says, that this the total friction angle of this kind of joint, which is rock joint, is so, and this OneNote is getting stuck. I cannot write anything. Okay. So what it is saying is, let's say you have some rock joint with, as I said, I is called asperity angle, and y is the friction angle of this material itself.
Hello, sir.
Okay. Yes.
So can you explain the graph once more, the above one?
Okay. So this is the result of this shear test, right? When we apply this normal stress, and then we try to shear it with a shear stress value. Okay. So I'm so sorry here. Can you see this this figure, or it's still some blank thing? Can you see it now?
Partially visible. Now it's visible, sir.
Yes. So what I was saying is, when you apply this, gradually increase this, this shear load on this uh, specimen after applying the vertical normal stress, then there is a relative motion, that is like this point and this point, they were in same vertical line before. Okay, now it is moving towards the right side. Okay, this point here. So that is the displacement, shear displacement. This is called shear displacement. But so if you plot this shear displacement versus the shear stress, what you are applying here, you get this kind of plot. Okay, this plot. And it reaches a peak value, the highest value here, and then it goes down. So this value, the highest value, is called your the shear strength tau for this value of sigma n. So this is our sigma n. So you get for this sigma n, what is this tau? This sigma n, what is this tau? This sigma n, what is this peak value? So you take this thing here, and as I said, we can plot it in our tau versus sigma n curve to get what is our cohesion C and what is the frequency of phi. Okay, then we have some Kn, normal stiffness, and Ks, which we are not discussing yet. This we will be not using in our mm, in this design for now. Okay. So is this clear?
Yes, sir.
Okay. So what I was saying is, let's say you know exactly what is the friction angle of this material, this joint here, or maybe what we can do. I don't know. So somehow, let's say we can take this rock specimen here and test it in the laboratory, okay, and get a friction angle of phi, let's say. Now, if we have some waviness in the joint, which is the is called our aspect angle I, okay, then the effective friction angle becomes phi equal to, this is let's say phi r plus I. Okay, is this clear? The effective, the friction angle. So,
Yes.
in other words, yeah. Anybody say something?
No, sir, I was saying yes, sir, only.
Okay. Yeah, it is getting stuck. Let's stop it here, and then we will be continuing. I thought like there was little bit here. I thought I can finish it today, and then we can quickly finish the institute stress. So our, as I said, our revision part from our rock mechanics that is done, and then we can move ahead. Okay, so let's stop it here. I don't know what is happening. I need to restart my computer. Okay, this is not doing anything. Maybe there is some internet issue. Any question up to